which affects about 1 in 100 people over the age of 60. The estimates vary, but we're thinking there are about 1 million people in the United States that have Parkinson's disease, and possibly over 5 million people in the world. And the disease is characterized by both motor symptoms, such as rigidity, a slowness of movement, an abnormal gait, and also non-motor symptoms, such as cognitive deficits, autonomic dysfunction, and depression. And there are treatments that ameliorate these symptoms. However, we still do not have anything that is disease modifying that will either reverse, will stop, or will slow down the progression of the disease. And that's why at the Michael J. Fox Foundation, we're very interested in this particular gene called leucine-rich repeat kinase 2, or LRRK2, as we like to call it. And the reason that we're so interested in it, and that we've invested already over $100 million into this potential drug target, are for the following reasons. So first, mutations in that gene have been shown to be one of the most common genetic causes of the disease. Second, the clinical manifestations of the disease in LRRK2 carriers is actually very similar to the non-genetic, more common forms of Parkinson's disease. So the possibility that a therapy that treats LRRK2 mutation carriers could actually possibly treat everybody who has Parkinson's disease. Also, it's very druggable. And that term is used when the pharmaceutical industry has a lot of expertise in being able to target that particular protein. So there are a class of inhibitors called kinase inhibitors, and the pharmaceutical industry is very good at making those classes of drugs. So it's low-hanging fruit to go after LRRK2. And finally, there's converging biology that shows that LRRK2 is playing a very important, if not a central, in Parkinson's disease. So we've made quite a bit of breakthroughs recently on LRRK2. We've been able to identify its substrates. A substrate is a protein that is either being turned on or turned off by LRRK2. We're also doing quite a bit of work on preclinical safety, which is showing us that it's possible that we're going to be able to move and do clinical development of these LRRK2 kinase inhibitors in people. But we still need more breakthroughs. And one thing that we still don't fully understand is what LRRK2 exactly looks like, what its atomic structure is. And we have a world-class team that's working on this problem here on Earth with a lot of different techniques. But we have one particular technique that it appears that we possibly might have better luck if we were to do it on the International Space Station under microgravity conditions. And this is looking at X-ray crystallography. And the basis behind that is that you're able to better understand what a protein could look like, and therefore, with understanding its structure, you can better understand its function. So you want to take the protein, make it into a crystal that amplifies the signal, amplifies the protein. You bombard it with X-rays, and then you're able to better understand what the protein actually looks like. This will help in two ways. First, it will help you better understand the biology of LRRK2. You can understand structure, you can understand function. And secondly, although the pharmaceutical industry has been pretty good at making LRRK2 kinase inhibitors, they've been doing it pretty much blind in the sense that they're using other kinases, other proteins that have been solved, and using that to make assumptions of what LRRK2 looks like and making drugs against it. And they're doing a good job with it, but we'll never know have the most optimal LRRK2 kinase inhibitor without a high-resolution atomic structure of LRRK2. And so I'd like to pass this on to Sebastian, who can explain to you a little bit more about the experiment on the ISS. Thank you.
Yeah, thank you very much, Marco. So I am part of the team that is applying the technique X-ray crystallography in order to solve the three-dimensional structure of LRRK2 protein. And our team is based in Oxford, UK, and in Frankfurt in Germany. Our general workflow is like, first we make a lot of the protein, then we produce crystals of this protein, then we analyze those crystals using focused X-ray beams, and finally we calculate the three-dimensional structure of the collected data. Our experiment on board the ISS, our aim there is to generate high-quality crystals. LRRK2 protein is huge. It's a massive protein, 2,500 amino acids. It comprises 7 domains. This